Okay, so in today's video we're going to continue where we left off the other day, talking about electron configurations. Last time we got through beryllium. Today we're going to pick up with boron and go through magnesium. And recall that we had talked about how with beryllium we'd got to electron configuration of 1s2, 2s2, and that basically filled up our 1s orbital. Our 2s orbital's now filled, and now we're along here to fill up the 2p, the 3s, the 3p as we need to. Okay, so again, keep in mind that here we filled up this orbital and this orbital. These each house 2 electrons. Well, if we look at boron, and we're talking about boron, boron has 5 electrons. So the first 4 electrons, yeah, we know where those guys are going to go. 1s2, 2s2. Following the Aufbau principle, we just build on the electron configuration of beryllium. But now this 5th electron, where is that going to go? The 5th electron is going to have to go into the 2p orbital. So the electron configuration of boron is going to be 1s2, 2s2, 2p1. And so if we draw our electron box diagram this time, we're going to have to draw it a little differently than we did before. Notice here I've drawn a box with 3 subdivisions in it. This is symbolic of our 3 m sub L values. M sub L is equal to -1, 0, and +1 for these 3 boxes. So there's 3 different orientations of the p orbital: px, py, and pz. And just by convention, we're going to put that electron with an upward facing arrow in this leftmost box. So the electron configuration, 1s2, 2s2, 2p1 for boron, we can represent it this way. So our kind of expanded notation. We can also represent it with this box, saying, okay, here we have an electron in the 2p, and you have those other filled boxes there as well you can draw. So what are the quantum numbers that describe the location of this 5th electron? Okay, remember, we're talking about the ground state. N equals 2 because it's a 2p. L equals 1 because it's a p orbital. M sub L is equal to -1 because it's the leftmost box. And M sub S is equal to +1/2 because it's an upward facing arrow. So what do we do then with the 6th electron? As we go to talk about carbon, we have to add a 6th electron. So for carbon, we know we have 1s2, 2s2, 2p2. Well, now we have some choices, because remember, boron is sitting there with this 5th electron in the 2p, and it's sitting there like this. So option number 1 is that we go along here and we go ahead and pair up this electron like that. Option number 2 says let's just occupy an unfilled box. Let's do this one right here. So here we have 2 choices here. Can you see how these are different? Here's where we're going to make use of something called Hund's rule. All right, now Hund's rule says that you're going to maximize the unpaired spins. These 2 electrons here are both, negatively charged particles, and Coulomb's law tells us that these 2 particles are going to repel each other. So there's a certain amount of energy that it costs us to have these particles in proximity to each other. So Hund rules tells us that wherever possible, give these guys their own orbital. So now we're going to split these 2 electrons up. We're not going to use this configuration. We'll use this configuration instead. And now each of the 2 electrons reside in their own orbital, say one in the 2px, the other in the 2py. And now they have a maximum. Okay, we've maximized the unpaired spins. So Hund's rule is all about maximizing the unpaired spin. All right. Wherever it makes sense. Okay. Now notice, with this configuration here, you never can tell the difference between whether the electron is in its own orbital or whether it has now paired up. but it's only when you draw the boxes that you can notice. But you're supposed to know when you see 2p2 that occupies its own orbital now. So what are the quantum numbers that describe the location of that electron? Well, n equals 2, because it's a 2 orbital, right? N equals 2. L equals 1, because it's a p. M sub L equals 0. Okay, by convention we've numbered these things from left to right according to increasing value here, our 3 M sub L values, and M sub S is equal to plus 1/2. Now we go over to nitrogen. Okay, we're building upon the previous electron configuration. So 1s2, 2s2, now we have 2p3. Okay, how many electrons do we have? 7. Okay, 7 electrons. So check yourself and make sure that you've accounted for the location of all the electrons. What's the box going to look like for this guy? Well, we're going to have, again, following Hund's rule about maximizing the unpaired spins. Here I'm going to have 3 unpaired electrons residing in the 2p orbital. Again, the quantum address here, n equals 2, L equals 1, M sub L equals plus 1, and M sub S is equal to plus 1/2, with it being an upward facing arrow. Now we go on to oxygen. Oxygen has receives an 8th electron now, so it has 1 more electron than nitrogen. 1s2, 2s2, 2p4. So now when we draw our electron box diagram here, this represents the 2p orbital. I have to place 4 electrons in that box. 1, 2, 3. This is kind of where we left off with nitrogen. We're now going to fill this orbital here, and the quantum address, quantum numbers if you will, of this last electron added, n equals 2, L equals 1, M sub L is equal to minus 1, M sub S is equal to minus 1/2. So for the first time as we cross the p block, we are using the downward facing arrow, so we use an M sub S of minus 1/2. Well, you can see what happens here as we move along here to fluorine is going to have an electron configuration of 1s2, 2s2, 2p now 5, and the electrons are going to be situated as such: 1, 2, 3, 4, 5. Spin up, spin up, spin up, and then down, down. So here's your 2p orbital. The quantum address of the last electron added, where's that last electron? It's right there. Okay, n equals 2, L equals 1, M sub L is equal to 0, and M sub S is equal to minus 1/2. So as we flip over here to neon, notice something special happens, and we've now 1s2, 2s2, 2p6. Now the reason I say it's special is, look, we've been gradually, as we moved across the second period, we've been filling up the p orbital, and now we've reached the place where it's at maximum capacity. We have now added the 6th electron here, so we have filled the orbital. No other electrons can go in there because we're out of unique set of quantum numbers. So following the Pauli exclusion principle, we have to move on now to another orbital. Okay, so the quantum address of this electron, I know you're getting sick of doing this, but it's just good practice. N equals 2, L equals 1, M sub L is equal to plus 1, and M sub S is equal to minus 1/2. Alright, so now the 1s is filled, the 2s is filled, the 2p is filled, and if you remember, now we're going to come along here and we have to move on. If we're going to talk about sodium, or we're going to talk about magnesium, or we're going to talk about any other element heavier than neon, we have to move on and fill the 3s orbital, and that's precisely what we're going to do as we move on to sodium. So sodium has an electron configuration 1s2, 2s2, 2p6, and now that 11th electron is going to have to go 3s1. Okay, and again, you should always be able to sum up these electrons here and get 2, 4, 6, and 11. So you should be able to always sum that up, 11. And that should equal the total number that you have. So that last electron added goes into 3s. And the quantum numbers being n equals 3, L equals 0, m sub L equals 0, m sub s is equal to plus 1/2. So where's the 12th electron going to go as we talk about magnesium? Well, you guessed it. Let's go ahead and just add that electron here for magnesium. Again, following the Aufbau principle of building up. 1s2, 2s2, 2p6, 3s2. Okay, we sum this up. We should get 12 electrons. Great, we do. And what we see here is that we've now filled the 3s orbital. We have a spin-up electron, we have a spin-down electron. Pauli exclusion principle says time to move on. Okay, n equals 3, L equals 0, m sub L equals 0, m sub s is equal to minus 1/2. So we're all filled up here. And if we do any more electrons here, if we move on to aluminum, we have to use more orbitals. So just by way of summary here, we talked about the ground state electron configuration for boron through magnesium. Again, followed the Aufbau principle again. And keep in mind, again, just let me emphasize, we're talking about the ground state electron configuration. So there's nothing to say that you cannot add some energy to a system, promote an electron that was in the 1s, say to the 2p or something, but that is an excitation, and that's not what we're talking about in this video. We're talking about ground state electron configurations. We're able to determine the 4 quantum numbers of the last electron added, just like we've got lots of practice doing that. And we followed Hund's rule. Hund's rule again telling us to maximize the unpaired spin. So this is what made us, when we are filling up our p orbital, we did this and not this. Okay, this was bad. All right. Thanks for watching. I hope you have a good day, and as always, get lots of practice and drop by office hours if you have any questions. Thanks.